Hello students, in previous lecture we discussed about some observations about Coulomb's law and what are the different comparison that we take in between electric force and gravitational force. Okay. So, in this lecture we discuss about an important and interesting topic, that is continuous distribution of charges. Okay. So, first thing, continuous distribution of charges, continuous distribution of charges. Okay. So, what do we mean by continuous distribution of charges? Okay. That means when we consider a system of closely spaced electric charge in form of continuous charge distribution, that means it is a system. Continuous charge distribution means a system of closely spaced electric charge. Okay. Suppose I consider this is a system. Okay. In this system there is a very large amount of charges and they are closely packed in that system. In such case we cannot use the formula of quantization, that is Q equal to NE. Okay. That means if I consider a macroscopic system means it is a very large system in which there is distribution of charge having in a closely packed manner. Okay. That means in such system the charges are very closely packed and there are very large amount of charges present in that system. Okay. In such case we cannot apply the quantization of charge. Okay. So, how we measure the charge of that system? Okay. So, a continuous distribution charge will arise if I consider a system having very closely packed charge over a very long range. Okay. Very largely packed or closely packed charges over a system. In such case we can use continuous distribution of charges. Okay. So, in continuous distribution of charges we always consider a macroscopic scale. Okay. That means the system must be a large system or macroscopic system in which there are a large amount of charges present in that system. Okay. So, in such case in order to measure the electric force between the different charges and in order to measure the total number of charges we can use the concept of continuous distribution of charges. Okay. Now, a question is that how can one measure that continuous distribution of charge? Okay. So, in order to measure the continuous distribution of a charge we divide the continuous distribution of charge along three categories. Okay. Depending upon the system. Okay. Depending upon the system we divide the continuous charge distribution into three categories. Okay. As a system may be one dimensional, a system may be two dimensional, a system may be three dimensional. Okay. So, depending upon the different type of system we divide continuous charge distribution into three different categories. Okay. So, the system which is one dimensional in nature, that is called line. Okay. The system which is one dimensional, that is called a line. Okay. The system which is two dimensional, that is called a surface. Okay. And the system which three dimensional, that means when you consider the entire volume then it is called the volume. Okay. So, depending upon the arrangement or depending upon the types of system we divide continuous charge distribution is like linear charge distribution. Linear charge distribution. Okay. Second thing, that is depending upon the two dimension, that is surface, that is called surface charge distribution. Okay, and for the entire volume, that is called volume charge distribution. Okay, so system of distribution of charges divided into mainly three categories. One is linear charge distribution, another one is surface charge distribution, and third one is volume charge distribution. Okay, as the charges are continuously arranged in that system, we have to take another measurement, that is charge density. Okay, as the charge is distributed over a long range. Okay, in such case we can use the concept of charge density. Okay, so that means we can say, in order to measure force due to, in order to measure force due to continuous charge distribution, okay, we can take help of two quantities. We can take help of a test charge, we can take the help of test charge, that is Q naught, and charge density. Okay, that means charge arranged in a unit range. Okay, charge density means that is the arrangement of charges in a unit range. Okay, so depending upon the distribution of charges, also charge density is also categorized into three different categories. Okay, first thing, is that charge density. So number one is about linear charge density. Okay, so as the linear charge density always takes the study of charges arranged continuously over a line. Okay, suppose I take on that line the total number of charge is Q. Q is the total charge. Okay, arranged over a line of length L. Okay, Q is the total charge arranged over a line of length L, and in such case the linear charge density lambda. Okay, the linear charge density lambda defines the total charge over a unit length. Okay, so linear charge density we may write the total number of charges over a unit length. Okay, so that is called linear charge density, that is lambda. Okay, or simply we may say linear charge density is charge per unit length, charge per unit length. Okay, charge per unit length. Okay, so that is called linear charge density. Okay, and linear charge density is denoted by lambda. Understand? Second thing is about the surface charge density, but when we consider a small range, okay, that means over that line, if I consider a small length, that is dl, on which the charge is dq, in such case the density lambda is can be written as dq over dl. Okay, so if I take a small length over that line L of length dl, and in that dl length the total charge will be dq, then lambda will be dq by dl. Okay, so what is the unit of lambda? So generally unit of lambda will be coulomb meter inverse. Okay, so unit of lambda will be coulomb meter inverse. As we take q by L, charge per unit length, So that's why it takes the unit as coulomb meter inverse. Okay. Second thing is that about surface charge density. Surface charge density, and it is represented by sigma. Okay. So surface charge density is generally represented by sigma, and when we consider the arrangement of charge over a surface of surface area S, okay, suppose S is the surface area of that surface on which there is a large amount of charge Q is distributed continuously, okay, and in such case the surface charge density can be defined as charge per unit area. Okay. So that is surface charge density is charge per unit area. Charge per unit area. So that's why we can write surface charge density equal to Q upon S. Okay. Q upon S. S is the area of that surface. Q is the total charge of that surface. So sigma equals to Q by S. Okay. If I consider a small area ds in which there is a small charge dq, then in such case sigma equal to dq by ds. Okay. So what is the unit of sigma? So unit of sigma equals to coulomb meter to the power minus 2. Okay. Coulomb meter to the power minus 2. Understand? So that will be the unit of sigma. Okay. So that is surface charge density. Okay. Charge per unit area. Okay. Third thing is that volume charge density. Volume charge density, and volume charge density is represented as rho. Volume charge density, that is rho. Okay. And when we consider a volume charge density, that means we can say distribution of charges over an entire volume element. Okay. Suppose I take here a volume element having the volume V. Okay. Suppose I consider a volume element like Q in which the total charge is Q. Okay. So in such case the volume charge density defines charge per unit volume. Charge per unit volume. That's why rho equals to Q upon V. Okay. So rho equal to Q upon V, and if I consider here a small unit volume in that surface containing the charge dq having volume dv, in such case rho can be represented as dq upon dv. Okay. And what is the unit of volume charge density? So unit of rho equals to coulomb meter to the power minus 3. Okay. So coulomb meter to the power minus 3, that is the unit of volume charge density. Okay. So volume charge density is the charge per unit volume, and this can be considered when we consider a distribution of charge over an entire volume. Okay. So there are three different charge density. One is linear charge density lambda, that is charge per unit length. Another thing, that is the surface charge density sigma, that is charge per unit area. And third one is volume charge or the volume charge density, that is charge per unit volume. Okay. So now take calculation of force, okay, due to a continuous charge distribution. Okay. So now take the calculation of force due to a continuous distribution of charge by taking the help of a test charge q naught and the linear charge densities. Okay. Force due to continuous distribution of charges. Okay. So first we take linear distribution of charge. Linear distribution of charge. Okay. So in order to calculate the linear distribution of charge, suppose I consider here a line of length L on which a large number of charges distributed uniformly over that line. Okay, a large number of charges distributed continuously over that line. Okay, and a test charge q naught. Okay, a test charge q naught is placed at a distance of r. Okay, at a distance of r from that line. Okay, so if I consider the total number of charge on that line is q, small q, and length of that line, suppose I take the line as AB, length of AB is L, then what will be the linear charge density? So lambda equals to q by L. Okay, so lambda equals to q by L, that will be the total linear charge density. Okay, now let us take a small length. Okay, suppose I mark here a small length whose length is dl. Okay, so dl be a small length. Okay, and on that dl there is a small charge dq. Okay, there is a small charge dq arranged in the length dl. Okay, so that's why the linear charge density, that will be dq by dl. Okay, so linear charge density may be dq by dl. Okay, so if linear charge density is dq by dl, then what is dq? So dq equals to lambda dl. Okay, dq equals to lambda dl. Okay, suppose the test charge q naught is at a distance of r from the length L, and when we take the calculation of force between dq and q naught. Okay, and if dq and q naught are in air medium, then what happens? There is a small force act in between dq and q naught. Okay, as dq equals to lambda dl, and what is lambda? Lambda is linear charge density. Okay, dq is the small charge on the length dl. Okay, so that's why dq equals to lambda dl. Let us take that is equation 1. Okay, suppose dq and q0, okay, may act a force, that is df equals to 1 by 4 pi epsilon naught dq into q naught divided by r square. Okay, so what is the total force on q naught? Okay, so here we have to measure the net force on q naught because of the total charge on length L. Okay, if dq is continuously distributed, okay, if dq we take, this one is dq, another one is dq, another one is dq, another one is dq over a long range. Okay, and if we divide that length L into a large number of dLs, okay, then the net force on q naught because of the total charge will be obtained by integrating this result. Okay, so what is the net force? So net force on q naught due to the charges on L is F equals to integration df. Okay, integration df over a length L. Okay, so because if we substitute here the value of dq, okay, so that equals to 1 by 4 pi epsilon naught, the value of dq is lambda dl. So let us take here q naught by 4 pi epsilon 0 lambda dl divided by r square. Okay, that's why the force depends upon the length. Okay, the force depends upon that short length. Okay, so net force will be obtained by integrating the small force because of that small elemental charge dq. Okay, so F equal to integration of df. Okay, suppose I take here vector form, that will be r cap. Okay, so that will be integration over the total length q naught by 4 pi epsilon naught lambda dl by r square r cap. Okay, so that will give the total force okay. So, this will be the total force because of a linear charge distribution. Understand? Now, take the discussion of force due to a surface charge distribution. Surface distribution of charges. Okay. Suppose I consider a surface of surface area S on which a large number of charge is distributed within that surface. Okay. So, this is the distribution of charges within the surface having the surface area S. Okay. And there is a test charge Q0 at a distance of r. Okay. And if we consider a small area that is ds on which there is a small charge dq. Okay. In such case, the surface charge density sigma equal to dq by ds. Okay. So, that is why dq equal to sigma ds, equation 1. Okay. So, now take the measurement of force in between dq and q naught. Okay. So, force between dq and q naught is df equals to 1 by 4 pi epsilon naught dq into q naught divided by r square into r cap. Okay. So, substitute the value of dq. So, that is why df equals to q naught by 4 pi epsilon 0 sigma ds by r square r cap. Okay. So, now the force depends upon the surface element. Okay. Force depends upon the surface element. So, that is why when we measure the net force on the charge q naught because of the total surface, in such case the total force can be obtained by integrating the equation 2. Okay. By integrating equation 2, that is net force on q naught is F equal to integration over S, that is df. Okay. So, that is why integration over S q naught by 4 pi epsilon 0 sigma ds by r square into r cap. Okay. So, force due to a continuous charge distribution equals to q naught by 4 pi epsilon 0 integration S sigma ds by r square r cap. This is the expression for force due to a surface charge distribution. Understand? Third things is about force due to a volume charge distribution. Number 3, that is volume charge distribution. Okay. Suppose I take a volume element having the volume V. Okay, on which there is a large number of charges arranged on that system in a continuous manner. Okay, and a small test charge Q0 is at a distance of r from that volume element. Okay, and if I take here a small volume, if I take here a small volume of volume dV containing the charge dq. Okay, so in such case volume charge density, that is rho equal to dq by dV. Okay, so that's why dq equals to rho dV. Okay, so dq equals to rho dV, so that's rho. And if I take two different case, that is force between dq and q naught, then dF equals to 1 by 4 pi epsilon naught dq into q naught by r square into r cap. So that's why q naught by 4 pi epsilon naught, substitute the value of dq, that is rho dV by r square r cap, equation 2. Okay, so net force can be obtained by integrating equation 2. Okay, so net force on q naught is d total force, that is F vector equal to integration over V, because the total force